A very good morning to one and all, invited guests, faculty members, participants from various colleges across the country joining in offline mode, as well as the ones joining in the online mode. On behalf of the Department of Mathematics, IIT Roorkee, I extend a very warm welcome to all of you to the International Symposium on Recent Advances in Computational Analysis and Modeling, organized by the Department of Mathematics celebrating 175 years of IIT Roorkee. Without further ado, I now invite our chief guest for the day, Deputy Director, Professor Manoranjan Parida, IIT Roorkee, onto the dais. I now invite Professor Apurva Sharma, Dean of Academic Affairs, IIT Roorkee, onto the dais. I now invite Professor P. Bera, Head of Department, IIT Roorkee, to the dais. I now invite Convener Professor Uday Singh onto the dais. I also extend a warm invite to the co-conveners, Professor Shiv Kumar Gupta and Professor Ameya Kumar Nayak, onto the dais. I now request Professor P. Bera, Head of Department, to welcome Professor Parida with the bouquet of flowers. I now request Convener Professor Uday Singh to please invite Professor Apurva Sharma with the bouquet of flowers. I now request all the dignitaries on the dais to proceed for the lighting of lamp. Due to security reasons with the fire alarm, we are having the electric lamp lighting. Thank you, sir. Thank you, everyone. I now request everyone to please stand up for the institutional Kulgeet. I now request Professor Shiv Kumar Gupta, co-convener, to address the audience and welcome them all to the symposium.
Please take your seats. Professor Parida, Deputy Director, IIT Roorkee. Professor Sharma, Dean Academics, IIT Roorkee. Professor Vera, Head of Department. My colleagues, friends, and participants from all over the world. A very good morning to all of you. On behalf of Mathematics Department, I welcome you all in the symposium, in this international symposium on recent trends in computational modeling. And I hope that your stay will be comfortable here in IIT campus, as IIT Roorkee is known for its hospitality. And during this visit here in this symposium, I hope that you will also interact with different faculty members here in the institute to collaborate and to discuss research problems if you have. Thank you very much.
I now request Professor Uday Singh, convener symposium, to address the audience.
Professor Manoranjan Parida, Deputy Director of IIT Roorkee, Professor Apurva Kumar Sharma, Dean Academic Affairs of IIT Roorkee, Professor Premanand Vera, Head of the Department of Mathematics, IIT Roorkee, my co-conveners, Professor Amya Kumar Nayak and Professor Shiv Kumar Gupta, and Professor UV Kahaler, who is online with us, and he is the President of International Society on Analysis, its Application and Computation. So we are thankful to Professor UV Kahaler for joining us online. And esteemed speakers and chairs of different sessions of the symposium, present offline and online, dear participants, my faculty colleagues and research scholars. I am grateful to you for accepting our invitation for attending this inaugural function as well as the symposium. This 5-year-long symposium on computational analysis and modeling is being organized under aegis of IJAC and in a very specific year, that is 175th year of our institute and 75th year of independence of India. The main aim of this symposium is unique in its emphasis on intersection between analysis, applied geometry, scientific computing, scalable algorithm, and software management. The symposium provides a forum for communication among the applied mathematician, computational science, and engineering communities. The goal of this symposium is also to bring together eminent scientists and mathematicians from all over the world working in the area of applied mathematics, analysis, and computational mathematics. Contemporary challenges raised by recent advances in the area of mathematics will be confronted with state of the art. Mathematical and computational techniques, computational approaches are the premier interdisciplinary platform for the presentation of new advances and research results in the field of science and engineering. Our speakers, session chairs, and participants are from different geographical regions of the world and belong to different areas of mathematical science. The participating mathematicians are from institutes of international repute, such as MIT, DTH, Zurich, Duke University, etc. Institutions of national importance in India, such as IITs, IIT, University of Eminence like Banaras Hindu University. Professor Misra is with us. So there will be total 20 invited talks by various speakers and 8 selected presentations by the participants. Each expert talk will be of 1 hour duration, followed by a discussion of 10 to 20 minutes. I hope this organization will help us in establishing a strong relationship of our department with other institutions, as well as showing the presence of our department on the globe more effectively. So once more, I welcome you all. Thank you so much.
Thank you, sir. I now request Head of Department, Professor Premananda Bera, to welcome the audience on behalf of the department.
A very good morning to everyone. Distinguished speakers, Professor Pde, Dean and Deputy Director of the Institute, Professor Sharma, Dean Academics of this Institute, conveners and co-conveners of our departments, Professor Uday Singh, Professor Shiv Kumar Gupta, Professor Amir Kumar Nayak, my dear participants, colleagues and staffs. It's great pleasure to welcome you in this 5-day symposiums on recent advances in computational analysis and modeling. It is a part of our 1-year program, that is celebration of 175 years of IIT Roorkee. Although this institute is very old, that is 175 years, we started in 1846, but our department came into the picture in 1960 only, with our own identity, please. Previously, this department was a part of the Department of Applied and Pure Mathematics, Physics and Chemistry. In 1959, the provisions of research came into the picture, in the university, which facilitate and encourage to do research in the university. And the first PhD in this institute came from mathematics department as well as geological departments in 1962. From that time onwards, department was familiar with running with 2-year applied mathematics, MSc applied mathematics, and research, please. It continued for long periods. In 1991, they introduced one more discipline, that is a diploma, PG diploma in
computer applications. It also ran for a couple of years. But later on, this course was basically converted, not converted, basically we invited another program in the name of Master of Computer Applications. And also, department initiated another program that is Master in Philosophy, MPhil in mathematics space. But it didn't sustain for a long period. MPhil was again, we mapped to the 2-year MSc in industrial mathematics. From 2001 to 2007, department used to run 3 master programs. 2-year applied MSc mathematics, 2 years industrial MSc mathematics, MCA, Master of Computer Applications. The Master of Computer Application was a successful program, but the intake of this program, for this intake of this program, we used to conduct a separate test, please, an exam. Then department thought to change these programs and initiated a 5-year integrated applied MSc mathematics in these departments. Where intake was from IIT JEE. No doubt, it was a very much successful program. Our students used to be well placed. From job perspective, also it is very good. And in the meantime, our industrial MSc programs was closed because of some job crisis. And 2-year applied mathematics in MSc also renamed simply MSc mathematics because there is a conflict in the name. Our students used to face difficulties in getting job in different universities of this country. So we started simply MSc mathematics and integrated 5-year integrated applied mathematics, MSc mathematics please. Again, in the time space, to attract the good students in the department and seeing the scenario of the job, we also change our programs. 5-year integrated applied mathematics to 5 years integrated BS MS mathematics and scientific computing. This program we have started in 2021 July session. Regarding research in our departments, at present, department having more than 120 PhD students and 10 postdoc students place. Our colleagues are completely involved in teaching as well as research. The research area we can split into mainly 5 categories. The first, I can say, differential equations, dynamical systems, and computational analysis, algebra, geometry, and number theory, analysis, complex analysis, analysis, operation research and statistics, financial mathematics, and visual numerics. In conclusions, I will say to all the participants, use this facility and explore your research area. Don't be shy. Listen carefully to all the talks. If you have the questions or queries in the end of the talk, you can discuss and clarify it, please. Don't hesitate. I wish all the best in these 5 days programs. Thank you.
Thank you, sir. I now invite Professor Apurva Sharma, Deputy Dean of Academic Affairs, to address the audience.
Thank you. Professor Pde, Deputy Director of this institute, who happens to be the director also today, officiating as director. Professor Bera, Head of the department, my colleagues, Professor Gupta, Professor Uday Singh, and Professor Nayak, my other colleagues in the audience, participants, and all other participants and resource persons who connected to us virtually. A very warm welcome to you all. Warm in the sense, not as far as the weather is concerned, okay? My heart, as far as my heart is concerned, okay? And good morning to all our India or Asia subcontinent. And good evening to our US colleagues and, of course, other part of the country, our world. Yes, we are here today in a very important event, an international symposium, which is like part of a series of events to mark our 175 years of existence as an academic entity. Yes, we have moved through a long journey and still we are young. I always feel we are 175-year-old young institute. Probably I'll tell why we are young. And during this journey, we have evolved every day and we have crossed many transitions. We have come through different transitions. Probably Professor Bera has given a very good account of the different transitions, what the Department of Mathematics itself has gone through. So many courses added, so many courses, programs like removed, and then again added few other things. And the latest being introduction of the BSMS program, 5-year program, with exit option after 4 years. And this shows the progressive thinking of the department, and of course with the help of the institute. And at the time of when the institute is planning for revision of curriculum, UG curriculum, the Department of Mathematics thought before the time, and they came up with an advanced version of their UG curriculum with a different format, which is unique to the institute, kind of BSMS program, and that too with renewed program or curriculum and renewed syllabus. That's very welcoming step, and that shows the progressive nature of our institute. Then while going through the timeline, ours is an institute which actually came out of, which actually born out of necessity, and that too while addressing a very big social problem. As you know, this our global participants also will be knowing, most of them will be knowing, perhaps. We are nearby one canal known as Ganga Canal. And it all started in 1942 when the Ganga Canal construction was started. And there was no manpower. Manpower in the sense, technically qualified manpower who could help in those construction activities. Professor Pde, being from that field, will be knowing all those things better, all those details better. But as far as I know, it was that necessity to create technical manpower, this great institute was seated. And in 1847, this institute was born, Of course, at that time, it was Thomason College of Engineering, and it was like that till 1947. In between, there were a lot of changes. There were new programs added. There were upgradation in the programs, diploma to like graduate programs. Then this institution affiliation was like with Kolkata University in 1847. Then it was changed to the affiliation was with Allahabad University in 1894. And then from 1948 onwards, this has become an university of itself that is known as University of Roorkee. However, it was not the end. Then in 2001, 21st September to be very precise, so it was like converted as one of the IITs. As all of you know, IITs are like institutes of national importance. And today we are here as an IIT. And today we are offering 16 undergraduate programs, couple of like integrated master's program, as many as 55 master's program, and a PhD. It is offering PhD almost in all cutting edge areas. And this institute is a home of 9,200 plus students being taught by 500 plus faculty members. That's incredible. We started with training in civil engineering department, or civil engineering specialization, and now we train students in as many as 55 master's program apart from others. Today we are an institute with 23 departments, one school, and all these departments and schools, they are offering various programs. And today our institute is like having faculty members whose like citation per faculty is among top 3 in the country. And it is a very happy news that we have jumped 35 places in the overall QS ranking with reference to last year. So that's kind of incredible journey. And it's also incredible to see all of you here for this academic event, which is being organized by the Department of Mathematics. In spite of very severe summer here, our faculty colleagues and students, they have taken a very enthusiastic stage and efforts, put a lot of efforts to organize this big event, which is globally spread. I was told like 112 participants have confirmed their participation, and 20 speakers, as many as 20 speakers are delivering their expert talks in this symposium. A true international symposium indeed. I'm very happy to see this event, and I wish all of you to enjoy this program. I wish the symposium a very success, and I wish you to enjoy the 175-year-old Vermont created by this institute. Thank you so much.
Thank you so much, sir. It gives me immense pleasure to also welcome with us President Isaac, Professor Uwe Keller, who is the President of International Society for Analysis, its Application and Computation, joining us virtually from University of Aveiro, Portugal. We welcome you, sir. Please address the audience.
Hello, everybody, dignitaries and participants. The International Society for Analysis, its Applications and Computations originally was envisioned back in the 1990s as a kind of elite scion. In the meantime, it became much more than that, and so we have nowadays members from more than 80 countries in the world. And a large part, one of the principal goals of our society is to promote our field, to exchange ideas, new trends with many countries and many participants and many people with a passion for our field. And therefore, we are more than happy when Professor Uday Singh suggested to organize this symposium under our auspices. And I'm more than happy to welcome you all to this and thank the organizers for this wonderful conference, and can only wish you all one thing. In these 5 days, use the time, listen to the talks, don't be shy, ask your questions, get new ideas, establish projects, and maybe get some great ideas yourself out of it and enjoy all the things around. Thank you.
Thank you so much, sir. I now invite Deputy Director, Professor Pde, to inaugurate the event with his kind words.
Good morning and good evening to attendees. We have a global presence all around the world to this international symposium on recent advances in computational analysis and modeling. A warm welcome to Professor Uwe Keller, President ISAC, University of Aveiro, Portugal, Professor Apurva Kumar Sharma, my colleague and Dean of Academic Affairs at IIT Roorkee, my other faculty colleagues, organizers of the event, students. So this symposium is part of our 175 years year-long celebrations. So different departments have conducted a series of conferences, and we are very happy that Department of Mathematics in its new building, they have shifted to this building recently, and they have hosted this very elite kind of activity. So my compliments to the department for organizing this event. And I wish it has been possible that IIT Roorkee and ISAC, they have done the event in a collaborative way, and I see that the collaboration will grow in future. I would like to compliment my young faculty colleagues from Department of Mathematics, a very dynamic team of young colleagues, Professor Premanand Bera, Professor Uday Singh, Professor S.K. Gupta, Professor Amiyan Naik. So for arranging this very impressive event with galaxy of eminent mathematics faculty from India and abroad. And our attendees, it spans some like 10 IITs, Banaras Hindu University. Professor Mishra is present in person, so a special welcome to him from NITs and other universities. And I'd like to appreciate support of our speakers from MIT, ETH Zurich, Duke University, Florida, Wayne State University, University of Bath, Bologna University, Ghent University. And I also acknowledge participation and support of Dr. Rama Govindarajan, Director ICTS. This rich scientific program of keynote lectures and invited talks, it shall be very useful to the attendees of the symposium. There are good number of advices. It says that attend means in totality without allowing a single word to drop. And I see the young attendees, those who are planning to pursue a career in applied mathematics and scientific computing, they can really see a great value in this symposium. In this 175th year, we have started many initiatives. Professor Bera very nicely documented the historical evolution of different academic programs. At IIT, we expect that we evolve continuously. We start new programs, we start new research areas, and areas which are no longer relevant, they can always be dropped. That's the beauty of the academic system here. And I'm very happy that at the Institute, besides Department of Mathematics, we have created a new school of data science and artificial intelligence. which is sponsored by the Mehta Family Foundation. And we have also created the Department of Applied Mathematics and Scientific Computing at Saharanpur campus. IIT Roorkee is placed at 3 places. Besides Roorkee, we have our presence in Saharanpur and Greater Noida. And my faculty colleagues in the Department of Mathematics, they take great interest in publishing in various peer-reviewed articles in reputed journals. This symposium will provide the right platform for collaboration amongst researchers from different institutes, those are attending the event. In fact, what are the takeaways? So if those collaborations, both at national and at international level, if they happen, that's going to be the success of this symposium. And I'm sure the developments in mathematical and computational techniques will be useful in solving different grand challenges of human civilization. This institute started with one grand challenge, with the scarcity of water for irrigation. So the Ganga Canal project was very successful, and the prosperity in the western UP in the adjoining area is attributed to the development of that canal infrastructure. And I am sure the deliberations, the basic focus of the symposium will certainly help the various applied aspects. And once again, I appreciate all efforts made by the organizers of this symposium and wish the symposium a great success. With these thoughts, I declare the symposium open. Jai Hind.
Thank you, sir. I now invite co-convener Professor Ameya Kumar Nayak for the vote of thanks.
Good morning to all of you, and good evening to Professor Martin Bajan, who is sitting from MIT. Hello. And early good morning to European people who have attended this conference, symposium. On behalf of ISRACAM Organizing Committee and Department of Mathematics, first of all, I would like to thank Professor Ajit Kumar Chaturvedi, Director IIT Roorkee, and all institute administration, who has provided a wide support for conducting this event successful. I would also like to thank Chairman 175th years of celebration, IIT Roorkee. I would like to thank Professor Manoranjan Parida, Deputy Director, IIT Roorkee, for joining this inaugural session and put a lot of encouraging words, which really keep us in high tempo. We hope he will support in all aspects for smooth conduct of this international symposium. I would like to thank Professor Apurva Sharma, Dean Academic Affairs, IIT Roorkee, for joining this inaugural session and elaborated about the 175th years of glorious celebration of IIT Roorkee. Thank you, sir. His encouraging words are a huge support for this international symposium. I would like to thank Professor and Head, Department of Mathematics, IIT Roorkee, Professor Bera, whose continuous support and help makes this event successful. The eminent speakers and moderators of the symposium will be the largest contributor who have agreed to deliver the talk despite of their busy schedule. As we have seen, many of the speakers are involved in various editorial boards and administrative jobs. We are really thankful to all the speakers, moderators who have agreed to spend their valuable time for this event. The symposium will never be a grand event without the participants. We are thankful to them. We would like to thank Professor Uwe Queller, President Isaac, for being a part of ISRACAM. Back to Roorkee, I would like to thank the faculty colleagues in the Department of Mathematics. Without your support, the event will not happen. I would like to thank Professor and Head ICC and the staff members of ICC Roorkee for providing all kind of supports. I would like to thank Dean Srik and his team for helping to manage the project account. Thank you and thanks a lot, and hopefully we'll make this event a grand success. So next I would like to invite our convener to brief the event session. First of all, like the first speaker will be from MIT, USA, Professor Martin M. Bajan, and the hosting event chairman will be like Professor Amit Agrawal, Department of mechanical engineering, and he is also like one of the Vatnagar Award winner. So thanks a lot for being everyone here. Thanks.
Excellent.
I request everyone to please stand up for the national anthem. I request everyone to please stand up for the national anthem. I thank all the dignitaries for coming and gracing the occasion. Thank you, sir. Thank you so much for coming. We now begin with the session, the first session. All the dignitaries for coming in.
Please wait, and our session will start now. Yes, yes. So after that, high tea will be served there.
At 11. The participants are going to get their kits.
Please sit down. The session will start soon. Since the high tea will be after this session only. Leave चल रहा है. And the first speaker will be Professor Martin M. Bajan, Department of Chemical Engineering and Mathematics, E.G. Roos Chair Professor. And the session will be chaired by Professor Amit Agrawal, Department of Mechanical Engineering, IIT Bombay. So if Professor Agrawal is there, then he can just say hello to us, and I can just hand over the session to him.
Yeah, please. Okay. Okay, sir. Okay, sir. Okay, sir.
Then I'll send one more link to you. Maybe you can directly link it over, like join it over. Okay. Okay. Thank you for calling, sir. Sorry, Professor Agrawal is not able to join. I'll just take like a couple of minutes to send the link, and he will join soon. Sorry, Professor Martin.
No problem.
Hello, sir. I have sent the new link to you. Maybe we can check. In this message, I can send you.
I don't mind giving the talk without an introduction too, if that's easier.
Yes, sir. Yeah, SMS.
SMS, sir. Yeah. We are waiting, sir. You can start. Yeah. WhatsApp this number is yes, sir. Yeah. I'll send. Thank you. Yes. Thank you.
So, Professor Agrawal will join soon. So let us start. I'll just briefly introduce Professor Martin Bajan. Martin Bajan, the E.G. Roos Chair Professor of Chemical Engineering and Mathematics at the Massachusetts Institute of Technology. His research focuses on transport phenomena, electrochemical systems, and applied mathematics. After a PhD in physics at Harvard, he joined the MIT faculty in mathematics and then chemical engineering, where he has served as executive officer. And as the first digital officer, he was elected fellow of American Physical Society, the International Society of Electrochemistry, and Royal Society of Chemistry, and awarded the 2015 Gustav Prize in Theoretical Electrochemistry, the 2018 Andreas Akrivos Award for Professional Progress in Chemical Engineering, MITx Prize for Teaching and Learning in Massive Open Online Courses. So now I'll request Professor Bajan to start the lecture, and please share the slides as well.
Thank you so much for the invitation and for the kind introduction. I'd like to thank specifically Professor Agrawal and the organizers for the chance to present my work and discuss it with you today. So let me share my screen. Actually, it says the host has disabled screen sharing by participants. So maybe that needs to change on your end. It looks like I'm not allowed to share my screen.
Sorry?
I don't, it says host disabled participant screen sharing. So I'm not allowed to share my screen on Zoom.
In the down, you can just see the share screen option is there.
Yes, and if I press it, it says host disabled participant screen sharing.
No, if you just put your cursor on the share screen down in the down,
Yeah.
then automatically it will just like puts there. No,
Yeah.
not share screen.
Sorry, not share screen?
So just we are making you as host. Then after that, maybe it is possible, I think.
Okay.
Yeah. Yeah.
Okay, it says I'm the host now. Okay, great. Now this will work. Thank
Yeah.
you. Okay, great. So hopefully you can see me now. And I will get going there.
Now it is. I think.
Okay,
Yeah.
great. All right, so I hope everybody can hear me. Let me know if there's any problems. So again, thank you for the invitation. I'd like to tell you today about a particular topic in computational mathematics, specifically learning battery physics from images. And this is work mainly done in collaboration with the Toyota Research Institute, MIT, and Stanford through the D3 BAT Center, which I direct on data-driven design of rechargeable batteries. So I like to start with kind of a philosophical question. What do I mean when I say we can learn physics from images? Well, what does that mean? I think a good way to think about it is to go back to the beginning of modern science in the Renaissance, which one could say began with a problem of learning physics from images. The images in this case were telescopic images of the planets with respect to the fixed stars, which were recorded with great precision in, at the time, unprecedented amounts of data by Tycho Brahe. And it took several decades, actually, even after that data, for Kepler to recognize a pattern. He realized that the complicated motion of the planets going back and forth in retrograde motion relative to the stars, which people had tried to explain with complicated epicycles of circular motion, could be much more easily explained by assuming that the stars are following elliptical orbits with the sun at one focus. So that was really a problem of pattern recognition. But what that led to was an even greater insight, which was Isaac Newton's development of the laws of classical mechanics, F equals ma, force is mass times acceleration, as well as the particular force law for this example, which is the law of universal gravitation. And here I would make the distinction that, for example, if we had computers today, I'm sure that artificial intelligence could easily find the patterns in the data. So if we took all of Brahe's data and we said, imagine that there's some three-dimensional motion that when viewed from the perspective of the Earth at one point, explains these motions, I think we could probably discover those curves. But I'm not so sure that today's AI or machine learning would come up with Newton's laws. And that's not only because we have to formulate a certain set of equations, is that we actually have to define the variables. There are certain scientific concepts that have to be introduced, and that those concepts have transferability beyond the data. And so I think that's still a pretty challenging thing. And that's really what I mean by physics, actually. Now, what I think is possible today, and I will show you examples, sorry, my screen's not advancing. Here we go. Is that we can do something a little bit more modest, which is that we use our human intelligence or our, sort of knowledge of science to create a theoretical framework. So, for example, we might still start with Newton's laws. We might define concepts such as acceleration and some parameter called mass. But let's say we didn't know the universal gravitational law, so we don't know how those variables are related to each other. So within the context of that mathematical framework with various defined variables that can be compared to experiment, we can in fact use AI or machine learning techniques to learn those constituent relationships between the variables. And so that's what I mean by learning physics by inversion of images. So I'll be giving you some examples of that today in the context specifically of batteries, where I've been working on this topic for quite some time. So I started working on this topic long before I got interested in data-driven methods and anything really like image inversion, but doing kind of old-fashioned science. And to make a long story short, I started working on this around 2005 or 6. And by 2013, I'd already published a number of papers that led to simulations like the one shown on the left here, which is a nanoparticle of a certain battery material called lithium iron phosphate. And what you're seeing in the black and white there is the insertion of lithium into this particle, where white is essentially an empty crystal and black is a high density phase of sort of full of lithium. And what's special about this material is that it's phase separating. So rather than having individual lithium ions go into this material and diffusing freely throughout the system, they form stable phases, which then evolve and grow, nucleate, and form these interesting patterns. So already by 2013, we could do this kind of simulation entirely using combinations of experimental data and in particular, quite a bit of ab initio quantum mechanically calculated material properties, so predictive material properties. Now, I never thought in my lifetime that anybody would ever be able to see this dynamics, because we're really talking about complex, heterogeneous phase transformations at the nanoscale. But fortunately, around 2010, I gave a talk at Stanford, and a young professor there at the time, William Chu, in material science, got interested. And over more than 10 years now, we've been collaborating, and he actually has leveraged the state-of-the-art X-ray synchrotron facilities that are available at Stanford to do imaging of battery materials, including lithium iron phosphate nanoparticles. And I went on a sabbatical to Stanford in 2015 and 16, and by that time, William Chu's group was able to extract images like the one shown here, which are images of done by X-ray scanning transmission microscopy, STXM. So basically, with about 5 nanometer lateral resolution in every pixel, the X-ray goes through the particle, which is a platelet of about 100 nanometer thickness and 1 micron across. And as the battery is operating in a certain electrochemical cell that goes into the synchrotron, you can actually see the dynamics of lithium going in and out of every individual particle in that system. And so we have this set of images. And this led to this idea, well, could we actually start directly from the images and learn? Because it turns out that what we observed was pretty close to dynamics we had already predicted. In fact, if you kind of freeze it right there, it looks pretty similar. I was actually blown away by this. I wasn't even expecting that. But if you look closely at the particle on the right, it's pretty complicated. On the left, you have an ideal crystal shape. On the right, you see it's kind of more irregular. This black spot is actually a hole in the particle. So some of these particles are fractured. So it's sort of a messy system. And so the question is, can we start from those images and actually somehow extract the physics from it? So to tell you about the story, I'm going to spend more than half the talk at the end telling you, just really showing you a bunch of movies and showing you how the results look in doing the computations and learning these sort of simulation models for these materials. But first, I have to tell you about the background. Now, I know in this audience, you may not have that much background in, in electrochemical systems or batteries or phase transformations. There's a lot of more advanced concepts here. I'll try to explain them and kind of summarize some of the math for those who are interested. I'll refer to some papers so you can look at it more yourself if you're interested, and then we'll get to the results, which I hope you will find interesting. So first, I have to tell you a little bit about phase separation. So if you look at the voltage of lithium iron phosphate versus a reference like lithium metal in this case, then as a function of the composition or the content of lithium, so it's hard to read here, but this is X in lithium, X iron phosphate in the upper right. So as you go from left to right, you're filling the particle with lithium. And what you see is you have a voltage plateau on insertion and extraction of lithium. And what that means is actually that at either end of that plateau are stable phases of lithium at certain concentrations. The way to see that is shown on the left here. So if you've studied thermodynamics, you can imagine that if we look at the free energy of the system as a function of composition on the horizontal axis, then you may be in a situation where, let's say, especially at low temperature, you have a double weld potential. What that means is that there are two special concentrations that are the lowest energy of the system if it remains homogeneous, meaning uniform concentration. But if you imagine starting at 0 lithium and adding lithium to the system, first you go down in energy, but then you start to go up. And in this region in between the two minima, which are connected by a so-called common tangent construction, it is thermodynamically favorable to take, for example, a 50% concentration system and drop down from the blue curve to the red line, which corresponds to a 50-50 mixture of each of the two stable phases. And now the connection to electrochemistry is that the voltage at an equilibrium, that would be the open circuit voltage, is the change in free energy resulting from that reaction per charge transferred. And so mathematically, if the anode is not doing anything, and this is a cathode where the concentration is changing, then the voltage as a function of concentration is basically the derivative dg dc, where c is, or x is the horizontal axis, but with a minus sign because the electron charge is negative. So basically, the blue curves on the right for the voltage are the derivatives of the blue curves on the left at different temperatures. And the red curve, or the red line, which is the plateau, corresponds to a plateau in voltage. So then now you can understand that at the endpoints of that plateau are two stable phases. So what I'm showing you here is very well understood by material scientists, electrochemists, and it's one of the ways that they map out the phase diagram in composition of various electrochemical materials or battery materials. But what I've been working on for the past almost 20 years now is formulating dynamical mathematical models for non-equilibrium systems. And what's really special about electrochemical systems is that you can control the current. And so unlike other types of thermodynamic systems, like say driven by temperature, where you really can't so precisely control a heat flux, in the case of electrochemistry, you can take the system to whatever current you want, by controlling electrons flowing through the outer circuit. So here's just a little bit of math. If you're interested, I have a review paper from 2013 on my general formulation, which builds on phase field models from physics and material science, but adapts them for chemical systems, and in particular, electrochemical systems. And so the way to do the modeling is you start out by writing down a free energy functional for the system as a function of the various internal variables, such as, for example, the concentration. So here's an example to model those particles I showed before, where we have an integral over the volume of the homogeneous free energy, GH, that's, for example, that double weld function I showed you before, and then a bunch of other terms. So the next term is the so-called gradient penalty or gradient energy, and what it does, it basically assigns a certain energy wherever there's a sharp change in concentration. And so I like to think of that as mimicking the interfacial tension between phases. So if there's a high concentration, a low concentration phase that are near each other, then where there's a big gradient, that term very conveniently gives you a measure of the energy of that interface. Also, in solid materials, such as these battery materials, it's very important to take into account chemo mechanics. So as lithium inserts itself into the crystal, there's a misfit strain. So the lattice changes its shape and size. And so whenever there are gradients in concentration in the system, you have, for example, an expanded part of the crystal, a contracted part of the crystal, and that leads to mechanical energy, where sigma here is the stress tensor and epsilon is the strain tensor. And of course, you can add other terms as well, such as having to do with electric charge, electrostatic energy, and dielectric polarization energy, or other effects. There also, importantly, can be surface effects in these particles where you have, for example, the interfacial tension of a surface is a function of concentration, and also the normal vector prescribing the orientation of that surface. So once you have a chemical potential, once you have, a free energy, the chemical potential, which is the change in the free energy of adding a particle, is the functional derivative or variational derivative, first variation of this functional with respect to concentration. And that's very well known and is widely used in thermodynamic or phase field type modeling. But the new part in my work is to really connect this back to chemistry. So I write that the chemical potential is a reference value, mu theta here, plus kT times log of activity. So now the activity, which is an important concept in chemical reaction kinetics and thermodynamics, is now connected to these variational derivatives of the free energy. And if you carry out that variation in this particular example I gave you, you get the terms shown here, where, for example, the gradient term turns into a Laplacian term. And anyway, once you have chemical potentials, you can define both transport and reaction kinetics in a consistent way. Transport leads to the so-called Kahn-Hilliard equation, where simply the fluxes are driven by gradients of chemical potential. That's very standard. In fact, it's named after Kahn and Hilliard for their seminal work on binary metal alloys in the 1950s, but in fact, the same equation was written down and studied by van der Waals in the late 1800s, actually, and then essentially forgotten until Kahn and Hilliard, and also Ginzburg and Landau in physics. in the 1950s. Again, coming back to what's new here, you can formulate, and I did formulate, a variety of somewhat familiar equations from electrochemistry, such as the Nernst equation shown here, given the equilibrium voltage across an interface, or the Butler-Volmer equation for reaction kinetics, in a consistent way where the activities of the oxidized and reduced species and the electrons naturally comes in. And so basically these variational derivatives appear everywhere in the model. They appear in the equilibrium potentials, the reaction rates, and the transport. And so let me now show you some movies of what those models predict. So this is actually pretty old work going back to 2011 here. If you take this crystal lithium iron phosphate, like I showed you before, we were kind of viewing originally that crystal from above. And if you see in this cartoon, this material can be made in thin little platelets. And in the depth direction, we argue that there are very small gradients. There's fast transport and suppressed phase separation in the depth. So it's kind of almost like a 2D system when you look from above. Or if you take a slice of it, it's a 1D system. And so here's a simple model of insertion of lithium into this crystal. So it starts at uniform, but when you get to the so-called spinodal point, where you have a linear instability to phase separation, notice we now picked up the high density phase and the low density phase, which correspond to the endpoints of the voltage plateau. And on the right, you can see the voltage is simply following the plateau as one phase is being converted into the other phase. So this is at a low rate. But if you simulate the same system at a higher rate, shown here, then actually you kind of blow right through the spinodal point. You start to see an instability, but then it kind of goes away, and nothing, and phase separation is actually not achieved in that example. And in this model, if you go to an even higher current, then it's at some point phase separation is completely suppressed. Although if you stopped the current at a certain point in the miscibility gap, you would recover phase separation. So simply the application of the current changes the thermodynamics of the system far from equilibrium. It's a very interesting phenomenon. And in fact, my paper Faraday Discussions 2017 goes into great detail on the general theory of this phenomenon. If you're interested, I summarize here where it comes from. In this model, the reaction rate versus composition has a prefactor that is concentration dependent. So it's autoinhibitory or decreasing during insertion, and it's autocatalytic or self-accelerating during extraction. And that behavior leads to growth or suppression of instabilities leading to concentration changes. Now, I mentioned elastic stresses. And so if you repeat the same calculation that I showed here from a 2012 paper, you can do the same sorts of things where at a slow rate, when you insert in the crystal, looking down on the top facet now, you can see these stripes forming of the different phases. And if you go at a higher rate, those phases are again suppressed, and above a certain critical rate, they disappear. Now, I believe that the suppression phase separation is one of the reasons that lithium iron phosphate is an excellent high rate material, because these phase separations are kind of erased at high speeds. But at low speeds, you do get the phase separation, and this tilting you're seeing and these interesting patterns come from coherency strain. So basically fitting together the different pieces of the lattice to minimize the strain energy. And again, here's just a brief summary of this Faraday Discussions paper. Those of you who are mathematicians might be interested here. I talk about in this paper the general theory of stability of reactive chemical systems, and come up with a general stability criterion, one of which is a generalization of Gibbs stability criterion, that the so-called chemical diffusivity tensor must be positive. But much more interesting and more novel is a generalization of Prigoghine's condition for linear reaction models to a general nonlinear situation, including these electrochemistry models, where what I call the autocatalytic rate tensor has to be negative. So essentially the rate has to be slowing down as it progresses to be stable, otherwise it's unstable. And that can be, it's very common to see this sort of strong nonlinearity in electrochemical reaction rates. On that topic, I'll just briefly tell you a bit about electrochemical reaction rate theories, which are very important in this work, and which we would like to learn from images. That's where I'm going with this. So first of all, the standard model of electrochemical reaction rates is very simply Arrhenius reaction kinetics, where you basically think of kind of some charge, maybe an ion, which is hopping over a barrier, driven by the so-called overpotential, which is sort of the bias of the reaction tilting the barrier by applying an electric field across that interface. So that's a very classical approach. Going back to the 1930s, it's by far the most widely used, some would even say the only model essentially is ever used in electrochemical engineering. On the other hand, Rudy Marcus in the 1950s, in 1956 actually, first recognized that the Butler-Volmer equation cannot apply to quantum mechanical systems, because something like an electron, which is quantum mechanical, does not diffuse like a classical object over a barrier and drop down on the other side. It's in a quantum state, and it has a probability of tunneling to a nearby quantum state. And the physics of that is completely different. And essentially, he developed a theory of that, which led to quite a different dependence, where the dependence on the free energy change, or the overpotential, if you will, is actually more of a Gaussian shape instead of a simple exponential. And a parameter lambda called the reorganization energy comes in. And that's because the picture is that it's not that an electron kind of goes over some barrier to their side. Instead, it's that the initial and final states of the electron are fluctuating such that when they both fluctuate to a similar energy, the electron just tunnels immediately and isoenergetically to the new state. And subsequent work by Marcus and also experimental observation by Chidsey in 1990 verified that in the case of electrodes, you have to basically take this Marcus rate and integrate over the band structure of the electrode, so the different types of energies available, and also the Fermi distribution, just saying how all electrons are actually distributed in that system. And so there's this integral here. And by the way, I have a math paper 2014 that gives a nice asymptotic approximation of this integral as a simple formula, which I'll show you in a moment, which makes it a little easier to use. So basically, these are different theories that exist for quantum or classical ion transfer. In the case of batteries and intercalation or lithium-ion batteries in particular, people always use the Butler-Volmer equation, actually, until the work shown here. So I have a paper of 2014, actually an experimental paper, which was the first to point out that intercalation may actually be limited by electron transfers. So as shown in this picture in the upper left for lithium iron phosphate, it turns out lithium iron phosphate is actually an electron insulator. So it doesn't like electrons. So in order to insert your lithium ion, you need a compensating charge. And what we argued is that the rate limiting step is actually when the ion goes in, an electron has to reduce a nearby site in the crystal. In this case, would be the iron goes from +3 to +2. And in fact, lithium iron phosphate doesn't even work as a battery material unless it has a carbon coating. So basically you need to supply the electrons to the material and then they sort of hop in. And we argue that it would be according to this coupled ion electron transfer process. And the full theory of electron transfer I published with my student Dimitrios Fragadakis in 2020. And in recent work shown here on the right with my collaborator Yang Xiaohorn, we've been doing studies, more traditional electrochemical studies of a wide range of battery materials and finding that the overpotential dependence and concentration dependence appear to be pretty well described by this, this model. However, in a system like lithium iron phosphate, because of complicated phase transformations, it's really hard to tell if we have the right model because we don't know how to interpret the data. Because imagine if the system is phase separating, you don't really know what the active area is for the reaction. The reaction is is occurring at different rates in different places. And so if you make a macroscopic measurement of current and versus, let's say, voltage, it's pretty hard to interpret. So we have this theory, and it predicts this kind of different dependence on overpotential and concentration in the Butler-Volmer equation, which everyone is using. But it's very difficult to tease this out of actual battery measurements because it's so complicated and you only get to measure an integrated quantity. And this is where images come in. In fact, I will argue to you that the kinds of measurements we've accomplished here by looking at images give you insights in the system that simply would not be possible any other way. If you can't look into the system and see the distribution of concentrations as the system is driven far from equilibrium, there's no way to learn or frankly even measure the kinetics of the reaction. And so this really is a combination of artificial and human intelligence, because I would argue that a computer by itself couldn't do this. We need all the knowledge that I just showed you to be able to set up an inverse problem to essentially learn the details of the reaction, from large data sets. So before I get into actual battery nanoparticles, let me give you some examples. We have a number of papers, if you're interested in the mathematical methods, led by my former student Hongbo Zhao, who's now a postdoc at Princeton. And the first paper is called Learning the Physics of Pattern Formation from Images or Image Data. And so here are some examples. So for example, imagine that we have a pattern which is generated by a known model, in this case, various nonlinear partial differential equations or integral differential equations. So on the left, we see the Cahn-Hilliard equation I mentioned before for a certain kind of model that has a homogeneous chemical potential, like I showed you before, this kind of non-monotonic thing, like this blue curve here. That's the dashed is the actual true model. And then C here is the concentration field, and D of C is sort of an unknown diffusivity versus concentration, which in this case is 1 minus C, just sort of a linear dependence. So at the top line here, we show a simulation of phase separation according to this model. So if you start with a 50% mixture with some fluctuations, it then evolves into these sort of snake-like patterns of high and low density stable phases, okay, in this simple model. Now, in the second row, we see what happens if we try to do a simulation starting from a model which is not phase separating. So we take the initial data and we end up basically erasing that and getting completely wrong results. But if we apply a certain mathematical or computational procedure, in this case, it's so-called Pde Constrained Optimization, where we try to essentially find the partial differential equation that best produces simulated images that match the true images, or sort of the known images, to minimize the least squared error, essentially. And what you can see in the subsequent rows is that, excuse me, after only 10 or in the second row and 30 in the next row iterations, we can basically get simulations that look indistinguishable from the truth, which is the top row, using only 5 snapshots of the dynamics in this case. And both the blue and the red curves, the chemical potential and the diffusivity, have been learned with high accuracy, at least over the range of concentrations that are in the simulation in the middle. In fact, as shown in the lower row, we can also add noise to the data and still learn those functions quite accurately in this case. On the right, you can see we've also applied this to a variety of other phase transforming type models or pattern forming models, including Cahn-Hilliard, Allen-Cahn equation, and also for non-conserved order parameters, and also the phase field crystal equations, which are non-local partial integral differential equations. So it's a nice general method. There's a few different techniques we can use to do the mathematical optimization, such as forward or adjoint sensitivity analysis. That's essentially what we're doing here. And you can read about that in these papers if you're interested. Now, before I show you the battery problem, let me just impress upon you the generality of this method, which I frankly find just really amazing. So here's an example we still have not published yet, but we're working on it, which is to learn a similar phase separating model. In fact, it's the very same Cahn-Hilliard equation in a totally different situation of molecular dynamics simulation of a binary Leonard-Jones mixture. So what this is a simple MD simulation of 2 million atoms in a periodic unit cell in 3 dimensions. And the 2 million atoms are all broken into 50% of them are one type and another one are another type. So it's like a black and white or A and B. And the interactions are set up so that the A and B are repelled from each other, but the same type A and B are attracted to each other. So if you start with a mixture, then slowly the atoms fluctuate and they phase separate, very much like I showed you with the continuum model already. Now, if you take your 3D simulation on the left and you break it into voxels or cubes that are roughly the size of a little bit bigger than several atoms across, then you get this simulation on the left. But if I apply the methods I just showed you on the right, we can learn a continuum model, which is essentially indistinguishable from the molecular simulation on the left that's been coarse-grained at that sort of molecular scale, actually. And in fact, the chemical potential, which is the top plot, and the diffusivity are shown here. And so if you just simply know the right framework for the model, then you can learn these unknown functions, and we're essentially learning the physics. So rather than sort of traditional science, which would postulate a model, and then you do some experiment, and you throw out essentially almost all of your data and reduce it down to one number, like a diffusivity, here, by observing a system driven out of equilibrium and following the dynamics and generating a huge data set of images, we can actually learn the constitutive laws with tremendous accuracy. And it's actually, I was pretty amazed actually that even at the scale of only tens of atoms, that this continuum model actually works so well. I mean, this is a very classical model for phase separation. I didn't even expect it would work this well, you know, for an actual molecular simulation. So I think that's an interesting result by itself. But now let's come back to the batteries. Okay, so what you're going to see here is the same snapshots for the same particle I showed you before that were already available to us now almost 10 years ago. And what we've done on the top is to make a continuous movie out of those images by simply interpolating the colors. So red here is the particle is full of lithium, it's the high density phase, and green, it's empty of lithium, that's the low density phase, and yellow is in between. And we apply this learning procedure to the model that I showed you before with this sort of Cahn-Hilliard reaction type model that I described. It's technically a Butler-Volmer dependence, this hyperbolic sign in this case. But the important thing is that we fit 3 different functions, as I'll now explain. Before I tell you those results, let me just show you how well for this particle, we can learn the simulation on the bottom to make it match the experiment. And this is like an actual lithium iron phosphate nanoparticle with all of its defects and everything. And essentially, it's almost impossible with the human eye to even see a difference between the simulation and the experiment. And again, we have a hole right here. So these kind of colors that are forming near the hole are showing how, partly as a result of elastic stresses, the presence of that hole is influencing where the reaction can go faster or slower. I should tell you also here that the edges of the particle, the concentrations from the experiment are given as a boundary condition of the simulation. So we don't learn that, partly because the experiment has error at the boundaries, and also because phase separation is highly degenerate. And if you don't give it some kind of guidance from sort of a template on the outside, then you can get sort of the right overall dynamics, but it won't precisely match because you essentially have to orient the phases, like nucleate them in the right way. Anyway, so what do we learn from that? Even from this one simulation, one particle, and in fact, we only have 6 images here. That's it. Here's what we can learn. First of all, we learn the free energy that I showed you as a function of concentration. So we learn the thermodynamics, and you can see we get a double weld function. And I'll show you how it compares with the previous one we used. We also learned the reaction kinetics. So we learned this prefactor J0C, the so-called exchange current, which is sort of a decreasing function of concentration, a high concentration. So it has that autocatalytic or autoinhibitory behavior that I described before, but it doesn't look like the function that I had written down previously when I first did this work 15 years ago. In addition to that, we can do pretty well with just those 2 functions, but to get the really good match you see here, we also infer a spatial dependence f of x here for the rate constant. So basically using some eigenfunctions that represent that shape, we sort of assume, or we learn actually, this distribution of rate constant over the surface. And the variation here in the shading is by about a factor of 3. So basically, as we had already guessed in the original experimental work, there are fast and slow regions on this particle. Now, you might worry, this is overfitting. And honestly, we had these results already back in 2017, and we still have not published it. I'm actually very close, possibly this week, to submitting the paper, actually. And that's because I was not satisfied that this is a valid fit because of this tweaking of the rate constant. So I first of all wanted to see, is this valid? Can we find some physical evidence of this? And secondly, we need a much larger data set than just this one particle to really be convinced that we have this right. Because, for example, the thermodynamics and reaction kinetics should be universal. It shouldn't depend on the particle, while the surface heterogeneity will depend on the particle. So I can show you that even for this particle, later, my collaborators at Stanford and Will's group went back and measured the carbon coating thickness. And I already told you, for lithium iron phosphate, you need that carbon coating on the surface to make this material work as a battery material. And that coating is only on the scale of a few nanometers, up to say 10 nanometers thickness. So it's very, very thin. But it turns out that the carbon coating thickness map, which was done after we did this inverse learning on the right, the images are on the left of the carbon coating thickness, they correlate pretty well. So in fact, simply by looking at 6 images, we not only learn the physics of the material and the reaction kinetics, we actually non-destructively inferred or measured heterogeneity of the reaction rate over the surface. So I was completely blown away by this result. But it gets even better, because then we said, okay, we need to do this for a really large data set. So you're seeing here just part of the data set. So we had from the original experiments data for 63 particles cycled in and out lithium over a number of different currents each at different rates. And so it totaled over 100,000 pixels of good data that we ended up keeping and using. And what you see here, each of these pairs of images, on the left is the experimental image, and on the right is the learned simulation for that specific particle. And the little thing spinning around is the clock, because some of these particles are cycled at low rates and some of them are cycled at high rates. And in a number of cases, we have the same particles cycled at different rates. And we assume that the thermodynamics and reaction kinetics are the same for all particles, but each particle has a spatially dependent rate constant having to do with heterogeneity of the carbon coating on the surface. And what we do learn is that there's this autoinhibitory insertion rate. And in fact, what we're seeing right now is insertion. If you just kind of look with the naked eye, you see that it's fairly uniform. But if I jump ahead, here's extraction of lithium from the very same particles. And notice it's just obvious with the naked eye, there's much more pattern formation going on, because in that direction, the rate is autocatalytic and hence is destabilizing, and you're forming patterns more easily. Whereas when you insert lithium, you're suppressing pattern formation. Very consistent with the theory. So now if we put all this together, what do we learn? Well, in the top here, we see the red curve is the learned free energy function. And I believe this is the first, maybe ever, experimental measurement, if you want to think of it that way, of a non-equilibrium free energy landscape. It's impossible to study in an equilibrium experiment. If I create a system which is at the peak of this energy, it immediately drops to the minima and phase separates. So you can't really hold the system there. But because the movies of the images here follow the system out of equilibrium, being driven over the barrier and back down, essentially we can map out the free energy surface. So I think that's pretty interesting. And just for comparison, in this case, the dashed line is the function that I had been previously using, which is so-called regular solution model. That function is given here in red. And you can see it's actually it's reasonably close, but the barrier shape and height is a bit different that we learned. But to me, much more interesting actually is the measurement of the reaction kinetics, or exchange current versus concentration. And here we see that the learned model, which is the solid line, is extremely close to the prediction of that coupled ion electron transfer theory I showed you. And as I said, this is something that I think could not be measured any other way, because I showed you the system is incredibly heterogeneous. All the different concentrations are evolving at the same time. So there's no way macroscopically to just measure current voltage and try to infer the reaction kinetics. There's no way to get it. You have to look inside the system and just deal with that heterogeneity. And amazingly, it comes close to this theory. Now, how about the surface heterogeneity? So we looked at a bunch of particles, and here are the actual images of the carbon coating thickness done by auger microscopy. And if we digitize those in the colored pictures, here you see the red and the blue correspond to different thicknesses of carbon coating. And if we compare that, the middle curves, the middle plots here are the carbon coating thickness. The left images of the particles are the inferred rate constant distributions simply from looking at the dynamics. And you can see that, the red regions and the blue regions correspond with each other pretty well. So amazingly, for all of these particles, just by having these images, and it's only 6 or 7 images per particle, we learn the model and we non-destructively image the surface. And I don't think this has ever been done before for a heterogeneous catalytic surface, because there's many problems in chemical engineering, electrochemistry, where the net reaction rate that you're interested in is actually driven by microscopic heterogeneities. For example, you have like catalyst particles sitting on a surface, and really the way that microstructure interacts with the overall rate is a big question. And here you can directly measure it. So I think this is a method that has great potential and power kind of beyond just batteries, but in this case, we were able to do this for batteries specifically. So So that was a story that I wanted to tell you in some depth and with some mathematical details as well. And now I'd like to, in the next couple slides before I finish, show you a few more examples of learning physics from images, again, in the context of batteries, but for different types of images. So I just showed you images obtained by X-ray microscopy. So those are really at the nanoscale, and they're images in space and time. But in fact, you can apply the very same methods of model-based inversion to spectroscopic images. So for example, we can do X-ray diffraction. So again, my colleague William Chu, with a very, I think, beautiful paper, mainly experimental, just published last year in Nature Materials, looking at a material called NCM, nickel cobalt manganese oxide. It's another popular cathode material. And this material is nominally, or you might expect, much simpler than lithium iron phosphate. It's not a phase separating material. It's so-called solid solution material. So lithium goes into this material and just kind of diffuses freely. And that's known by a variety of methods. And yet, people had published a number of papers before our work claiming or giving evidence that there seemed to be at high rates some evidence of new thermodynamic phases appearing. And what's interesting is that if you look at these pictures in the middle, which show the vertical axis is time, the horizontal axis is the wave number of a certain X-ray diffraction peak, that if you slowly delithiate, so you're inserting into the crystal going downward here, you see that that peak moves smoothly, and there's only one value of it, sort of one peak. And that corresponds to basically the lattice slowly expanding or contracting at low rates as lithium is in this case taken out. Now, if you take out lithium quickly though, what you find is at a certain time now there's sort of a breaking up of those peaks, and it looks like there's phase coexistence, so people had observed before. And what we showed definitively in this paper is that this is a consequence, again, of this autocatalytic, autoinhibitory reaction rate for a material which is otherwise a solid solution material. So it's really the reaction rate nonlinearity that is destabilizing the system, but only during fast extraction of lithium. So on below is a simulation of a porous electrode using our model. And here you see extraction. From red is the full state, and now we're kind of emptying lithium. And notice it's very heterogeneous. In this case, the small particles are delithiated before the big ones. And then eventually they all finish. But if you now insert again, you find that it remains uniform. And so you'll see that movie play, and now the green is going to turn back to red in a more uniform way. And you can see the voltage being predicted here as well. And the reason, again, is that as you're inserting lithium, the rate is slowing down, it's autoinhibitory, and that's stabilizing. And when you extract it, it's destabilizing. And even with such results, we found that various reviewers and some colleagues were still very skeptical about this. And the real key prediction, though, was not just to do constant current, but to do, for example, pulses or interruption of current. So if you, for example, do insertion of lithium at a constant rate, or extraction, let's say, and then you turn off the current. Somebody who believes this is explained by nonlinearities in diffusion inside the particles would have to say that there's kind of a shrinking core of one phase being replaced by the other. So there are gradients inside the particles that are leading to this behavior. But we would say, no, it's from reaction kinetics. So the differences in concentration are between different places on the surface or between different particles. And so the way to test that is just simply to turn off the current. And if you do it quickly, then the particles just relax to their equilibrium state. And so if it's diffusion, all the gradients inside the particle should go away, and you should find all the particles look exactly the same. But that's not what we find, because it is driven by reactions. We find what I call Mosaic Instability. The particles just sort of snap into their stable phases, and they all have different concentrations from each other. And so that's verified there. And we actually did a Bayesian analysis to show that the reaction limited model was the only one that could explain this data. So I think this is actually a much simpler system than lithium iron phosphate. So we were able to get much more definitive results out of this one. But I think for this audience, maybe the most interesting thing is that we have a general mathematical framework, and we can start with X-ray diffraction patterns or spectroscopic data and still perform inversion. to find unknown properties of the model. Let me now move on to some other examples in batteries. Now we'll come back to spatial images again, but these are now not electron image, or excuse me, X-ray images, but these are actually optical images. Now, as you may know, the most important anode material, which is used in almost every lithium-ion battery, including all of your cell phones, laptop computers, electric vehicles, it's carbon or graphite. And an interesting thing about graphite that you may not know is that it's a phase separating material. So if I look at the voltage of lithium in graphite as a function of lithium content on the horizontal axis, we see plateaus like I showed you before, but instead of a single plateau like lithium iron phosphate, which corresponds to 2 stable phases at the endpoint, the voltage is a staircase, okay? And what that means is that at every end of one of these steps is a stable phase. And this is known. For graphite, it's known that there are many stable phases, and they correspond to different layers being filled of the structure and also various other patterns that could occur at lower concentrations. Now, a nice property of graphite, which also has been known for a long time, is that these certain special phases have different optical colors. So the full phase is kind of a yellow gold color, half full is red, and then 1/3 full is sort of a brownish color, or even bluish brown, and then empty is sort of a black color. And so, in fact, there were experiments done already more than 10 years ago, taking a graphite anode, unrolling it, and observing lithium going in and out. And you can see on top what the image looks like. And so those are basically different phases of graphite that I just described to you, going from a filling of basically near 0 to 30% to 50% to 100%. And actually below that are synchronized simulations from a theoretical paper from my group in 2014 explaining this phenomenon at a macroscopic scale. But I think much more interesting is that in later work in collaboration with Samsung, they did experiments observing at a much smaller scale the dynamics of the phase separation. So they basically drilled a little hole in the back of the current collector in a real Samsung battery and observed, lithiation in that system. And here's what you find. If you start with a system as empty, you first get the blue phase, which is 1/3, then you get the orange, which is 1/2, and then the yellow is 1 as the value of X in lithium XC6. So basically that's the concentration of lithium. So what you notice, it's not a smooth diffusive process. It's very much like I showed you before. You have these stochastic non-uniform phase transitions that are driven by the electrochemical reaction. And you do need the kinds of models that I've been showing you to be able to explain this behavior. Now, an interesting fact about this, though, which I think is an interesting, maybe general observation for those of you doing mathematical modeling, is that a model that doesn't take into account any of that phase separation can still fit the current and voltage. So it turns out there's classical models of batteries that don't account for any of these phase transformations that can still fit voltage data. And those have been around for a long time, pioneered by John Newman at Berkeley. So what we did in this paper, 2017, was on the left to simulate that experiment on the graphite particles at a certain high rate of charging. So let's say 6-minute charging, so-called 10C, up to 60% state of charge. And on the left, if you look as a function of position in the battery, the concentration at the surface of every particle is around 60%. So what it means is the battery charged kind of uniformly, and you don't really see any reason to have a problem. Now, why would there be a problem? I forgot to mention here, actually it's on this slide, I showed you this voltage staircase here. The 0 is lithium metal. And what that means is if the potential falls below 0, then lithium electroplating, making metallic lithium, becomes thermodynamically favored, which is a big no-no for lithium-ion battery. The way lithium-ion battery works is you want to insert lithium into graphite and then get it back again reversibly. You do not want lithium going into lithium metal. That gives you inefficiencies and ultimately even safety concerns. And it was already shown in the 2010 experiments that lithium metal can form at high rates. That's the silver color you see here. And in fact, it's clear looking back that it only forms on top of the yellow particles, which are full. And in fact, if you switch to our model, then in fact, when you do that same simulation of fast charging, you find that when you get to 60%, most of the particles are sitting at 50%, but near the separator, a bunch of particles had jumped to 100%, and those are the ones that are high risk of lithium plating. So what we showed in this paper is really, for the first time, why you cannot charge your batteries faster. And it comes down to all this physics that I'm trying to teach you here, and that we also are learning from images, which is that if you only have a model with diffusion and reaction, there's no way to explain it. Diffusion, transport, and reaction in these graphite electrodes are fast enough to sustain really high currents. You could charge in 1 minute, no problem. The thing is, if you do that, what the correct model gives you is that you will start to trigger side reactions that will rapidly degrade the cell and in some cases even cause safety risk. So what it means is you can charge fast, but there's no free lunch. You're going to also have the battery die faster. And so if you like a long life battery, you just can't charge that fast, actually. And this is the reason that right now, electric vehicles, for example, can't charge as quickly as we'd like. Or generally lithium-ion batteries, like for your cell phone, they charge them slowly overnight rather than charging in a few minutes while you're sitting there. It's not that we can't do it, it's just that the battery's not going to last. And this is the explanation, I believe. Now, we have pursued the same strategy of image learning here as well. So these are some experiments from my lab where we actually took a large single crystal of graphite and observed the colors of lithium intercalating, and also observed how at high rates lithium metal can nucleate and grow on the surface of the graphite particle, as we see in the lower left. And again, we can digitize these images and compare with our models and have now an additional model for the lithium plating nucleation growth, which is learned from the images and also from the voltage data. And we're able to get a reasonably good fit of, let's say, lithiation, and then a prediction of what happens when the material's at rest, and also during delithiation. This was published last year. So I think here we're starting to get really deep insights using this image learning method into very complicated problems and important problems in electrochemical systems. And now to connect this back to a theme I think you'll be hearing about in this seminar, the symposium, we in our group in this D3BAT Center, now led, and I say we, but mainly led by my colleague Richard Bratz, have been using machine learning methods directly on battery data for current and voltage to optimize battery use and predict battery lifetime. And in fact, Richard's group showed already a few years ago that simply by observing the first few cycles of a battery, and you apply machine learning methods to correlate with lifetime, we can actually sort the cells into good ones and bad ones and predict with pretty high accuracy which are the good ones, which is a very important breakthrough for industry, because one of the slowest and most costly parts of manufacturing is forming those cells through an early cycling, sort of stabilizing them, and also quality control, deciding which are the good ones, which are the bad ones. And it's incredibly hard to do that if you don't have this kind of data-driven approach. Now, what I have to tell you, though, it comes back to my story about the early days of science. What we did in this paper is like what Kepler did, is we're finding the pattern in the data. What I didn't tell you is that this data was generated by a dedicated facility that cost about $1 million to set up at Stanford through our center with Toyota. So just to simply generate the data, we had to cycle large numbers of cells for many months, in fact, even years, under controlled conditions. Only then could we make this sorting. But that's not what you need in real life. In real life, the batteries are used in different ways. When you form the batteries, in manufacturing, they're constantly changing the chemistry, the additives, the compositions. And so it's not feasible to do this kind of machine learning on a large data set every time. And that's where models come in, because I'd like to argue that all the stuff I showed you up until now is giving us the deeper scientific understanding, which is more like what Newton did. We're trying to learn the scientific principles that can transfer you to get away from the data. So you learn the models on one set of data, but we hope the models can be applied to a new set of data. So as the system is changing and you have very limited new data, you can still make predictions. And that's really the essence of science, in my opinion, is to generate transferable predictions. If it's just pure machine learning with a black box, to me, that's not really science. That's like curve fitting. Okay. So I'll finish then just by showing kind of a slide about D3BAT. So we are working on these kinds of problems across a bunch of length scales. If in the questions, I can show you a few more examples. We're also looking at acoustic emissions or sound waves coming off of batteries. We are looking at mechanical deformations of battery materials and working at a number of different scales, but still using this kind of hybrid approach of combining mathematical modeling and computation with large experimental data sets. And in that way, I sort of show my student Hongbo here, who has sort of combined in some ways what these three gentlemen from the Renaissance did in founding science as we know it today. So with that, I'll take your questions. Thank you.
Thank you, Martin, for this wonderful lecture. And you try to incorporate like the inverse modeling with the battery physics, and you have incorporated like the machine learning algorithm with all these stuffs. So I'll just request the audience if anyone has any kind of questions or queries. Yeah, please.
I guess it was all clear, right?
Yeah, she is coming. Just
Okay.
Hello, sir. Very good evening, sir. From Republic of India, I want to ask a question, sir. Can you suggest a chemical element that we can use in soft robotics if we consider soft robotics for space technology?
I'm sorry. Can I suggest another element for what?
For soft robotics.
For what vortex? I'm sorry.
Sir, I want to just ask that if there's any chemical element that you can suggest for soft robotics that we can use if we are planning to use soft robotics for space exploration or kind of space tech.
Well, okay, so I'm not sure I totally understand the question, but certainly for space tech, I think lithium-ion batteries are used and are interesting. There are other electrochemical systems that can be used, for example, for space propulsion, which have not very much to do with my talk today, but for example, there are ionic liquid propulsion methods that are used for spacecraft, for repositioning satellites, things like that. And also for long-term power, like, where you really need good reliability, you wouldn't necessarily use some of the batteries I talked about today, which are really designed more for portable electronics or, excuse me, or electric vehicles, on Earth with certain, characteristics, but rather in space, you need extremely high reliability. And you also may not have the same needs for, high power. And so there are, but still I would still generally other lithium-ion chemistries are the best way to go for, consistent batteries today. There's nothing that compares to it. Yeah.
Okay, so thank you, sir.
Sure.
anybody else? Any other queries? Anyone? Sorry? Online participants, anyone has any kind of queries, questions?
Hello.
Yes, hello.
Good morning to you, sir. As you showed in one example that the experimental image and your learned simulation, they were quite close to each other. So the number of parameters or the pixels that you would be using for learning that simulation must be very high. So is there any scope of overfitting in your model?
That's an excellent question. So, and really, actually, that's why we spent a long time working on this. And in fact, we have some theoretical papers on sort of, you know, how much data is needed to do this, which is shown here in the Journal of Computational Physics. But specifically for these battery particles here, if you only have one particle and here you have just a set of, let's say, 6 images, you can do pretty well. But it's really where we, I think, get much more convincing results is here. And this is not the whole data set you're seeing here. This is just a few particles. We actually have 63 particles, and some of them were cycled at multiple rates. You know, so there's much more data than what you see here. And while it may seem like overfitting, and I definitely worried about that. Like I said, we spent actually this project has been going now for about 7 years, and we're finally ready to publish the paper. So this is no small achievement, actually. It's easy to apply this method to simulated data, like I showed you. For example, in this like MD simulation, like I know what the truth is, right, and I know what the noise is, and I can try to fit it. But here, it's not so obvious. But the reason I think we ended up getting very good results is that there really are not very many parameters. So, for example, we have only 2 unknown functions that describe the physics. There's a reaction rate constant versus concentration, and there's a reaction rate versus position on the surface. The position versus over the surface is represented by some basis functions, and there may be even as many as like 20 or 30 parameters, those basis functions, and they are, for each particle, they're the same, but we are not allowed to change them at different rates. So if we cycle in and out at different rates, we have to use the same spatial dependence. The concentration dependence is the same for all particles. So for example, this blue curve you see here, which is represented by a couple polynomial, by some set of like Legendre polynomials, for example, there again, we have maybe 10 or 20 parameters are needed to fit that function. But that's the same function for all those particles. So the total number of parameters we're fitting here is vastly smaller than the amount of data that we have. Now, what you see here is that with this much data, where we have 100,000 pixels and we have in the order of, maybe 100 parameters or less, the reason it works is because we have the right physics. I already showed you in my first slide that the model that I proposed already many years ago, before any of this data, is actually pretty good. Like it's kind of already close. If you gave me these images and I knew nothing about the model, it would be extremely difficult to do this. And the reason is that if you know nothing about the model, certainly in mathematics, as many of you probably know, there are methods to learn PDEs from data. For example, you can learn the Navier-Stokes equations from observing fluid flow. The problem is that if you don't know any of the physics, if there's no framework there, then all you can really do is differentiate the data in space and time and look for essentially correlations between those derivatives. And that's how you learn the equation. But the problem is that here, because the X-ray scanning is pretty slow, we only have occasional snapshots of the dynamics. And during that time, the pattern completely changes, actually. It's not a continuous pattern as I show here in these movies. We've interpolated it. And in fact, this method works even if you just have 2 images. If you have the right framework for the model, and you only know the initial and the final, and each one of them is a fairly rich spatial image, you can actually learn that model pretty well. So basically, you should worry about overfitting, but I think what this shows is that if you already have good scientific insights into a problem, you have some idea what the model should look like, then you can get by with much, much less data than you might think. And the data can even be noisy, which is another interesting feature here, and you can map out that noise. And that's what we found in this case. Now I can show you other examples of this, kind of approach, and we don't always get it to look so perfect. And even for this data, we did many other things with this. We also found that we could learn the model reasonably well, even without doing any of the spatial stuff, and simply knowing only something that was measured in the original experiments, which was kind of what they call a uniformity coefficient. So it's basically how uniform is the concentration, some statistical measure, kind of like think of it like a variance. If we know the uniformity versus time, and we know, and that's all we have actually, and then we know like the voltage as well, and the voltage and current, we can actually infer the model reasonably well, even just from that. So basically, I'm showing you here near perfect agreement between the model and the simulation, and it's because of two things. We have a good model to begin with, and we have really good data. And if you put it all together, you know, and you learn it, like you can definitely fit that data. But what we've also shown is if you take away some of this data and you say, let's not even fit the surface reaction rate, let's just try to fit the thermodynamic free energy function and just the overall shape of the reaction versus concentration, you can still do pretty well, actually, with much more limited data sets. So there's kind of this trade-off between how well you can do in fitting and, you know, how much data you need and also how much model knowledge you need as well.
So another question in the chat box, it is there like regarding a BTMS. A recent technique is to capture the battery thermal field and any numerical model to compute the temperature fields.
Yes, so this kind of method can be applied to temperature. In fact, I personally first got interested in this type of approach in a thermal model. So my first paper on this type of thing from like 2016 or so, or I forget exactly when, is looking at the temperature profile from an infrared camera in a bar of material. For example, take a piece of aluminum and touch it to a cold plate, and you see the temperature changing color, changing. And with an infrared camera, you can see the profile. And in that paper, we basically backed out the thermal diffusivity and even the heat transport equation from that data. And also we did an optical camera at the same time, and we saw the slight changes in the shape of the sample, and we learned the thermal expansion coefficient from that as well. So you can definitely apply this approach of inverse learning, again, with a sort of modeling framework to quite different systems. I even have a bunch of other slides here. Let me just show you one other example. So we also learned here, this is a totally different set of problems, but still related to batteries. We learn the plasticity behavior of lithium metal from images. So here we have a certain rate-dependent quadratic yield model. So if you don't know what that means, like, don't worry about it, but it's a certain model of how lithium metal deforms plastically, which means essentially yields and starts to flow, okay, which happens very easily with lithium. It's actually a very soft material. And in this paper, 2021, we got, I think, the best results for lithium. Why is this not coming? Oh, there it is. Yeah. So for lithium mechanics, nonlinear, plasticity like this, by doing simulations like this, where we took like a foil lithium, put some very shapes of notches in it or holes, pulled it apart, and from digital image correlation, we have the strain field. And by essentially doing a finite element calculation of the mechanics and solving an inverse problem, we basically can learn the coefficients in this quadratic yield model. And this, I think, is by far the most accurate determination of the mechanical properties of lithium metal, which I think has been done to date. And again, it comes from using all of the data. So instead of just like in mechanics, you take an object and you pull it apart and you measure the total stress and strain and you walk away and you get an elastic constant or something like that, right? Here, we're taking a complicated geometry, we're deforming it, and we're observing with images the entire deformation. And by doing that, we have a much richer data set from which we can learn much more accurately rather complicated models. And in fact, we have actually validated that. And I just want to show you the kind of things we're doing with it. Now we're actually taking some collaborators who do experiments of sort of pressing lithium metal into solid electrolytes when they're manufacturing lithium-ion batteries. And the question is, how hard do you push to get good contact without having the lithium metal kind of break through the material and flow into it? And so we actually can do simulations like shown here with our learned model, which I think are actually probably pretty realistic, using actual reconstructed images of the solid electrolyte material from so-called FIB-SEM techniques. So this is just another example of this same procedure. Like you could, again, you would have a hard time doing this like somehow directly from a black box machine learning. But if you take all of our scientific knowledge, the equations and the concepts that we know how to define, like force, acceleration, reaction rate, and we put them into these inverse learning frameworks, I think that's a very powerful method. And if you start with rich image data sets like this one here, it's amazing what you can do with it, actually. Yeah, so.
Any other queries from the online participants? So I hope there are no further questions. I have a couple of questions maybe from my side.
Sure.
So you have used this chemical kinetics and like the charge transfer based on non-equilibrium like thermodynamics model.
Yes.
So have you incorporated this electrokinetic equilibrium conditions?
So I have not applied this method to electrokinetics per se, although another area of my research, which I didn't talk about today at all, has to do with modeling electrokinetic phenomena. In fact, that's actually used to be one of my main areas of research. In fact, I can sort of plug to you guys today that I just recently, last month, founded a new professional society called the International Electrokinetic Society, and our annual meeting is going to be held in Israel in 2 weeks. So if anybody's interested, let me know or find it online. But anyway, so in electrokinetics, we're concerned about charges in solution, which are often at the nanoscale in so-called electrical double layers. And when there are voltages or electric fields applied, then the fluid can get into motion, or if you have particles, they can sort of start swimming in electric fields by electrophoresis. And that's another field where we have a lot of scientific knowledge. It goes back, more than 100 years. But the models of that interface and the generation of flow are, somewhat empirical and pretty simple continuum models. That's well known. And I myself and many others have worked on developing modified models of the double layer, taking into account, for example, finite ion size, correlations in electrostatics, dielectric effects, etc. But we never quite know if we got it right, because it's kind of like I showed you here with the batteries. We only see the macroscopic consequences of all the microscopic interactions. We can't really directly measure them. I think it would be very powerful to apply the same methods I'm showing you here to that problem, and essentially take molecular dynamics and or experimental imaging close to surfaces and learn the structure, the models for the structure of the double layer and the generation of flow. And I haven't had a chance to do that yet, to be honest. Actually, right now, all the funding, all the interest is in batteries, and not as many people care about electrokinetics. So I'm definitely personally interested, but I need somebody to give me a grant to have some students working on that to really get deeply into it. But I think it's a great question, and there's definitely an opportunity for this kind of approach.
Yeah, I hope
these types of models and also just this inverse learning approach to be applied in that field.
Yeah, I hope you have started in 2002 to 2005 that electrokinetic equilibrium conditions, all the hypotheses, and you have written one chapter. I hope I have just followed you at that time.
Oh, great. Oh, well, thanks. Yeah, no, definitely. I've been working on that field I'm still publishing papers on that. In fact, I'll probably never stop working on that topic. It's an interesting topic, but I have not yet applied this method to that. I have applied the chemical potential ideas I showed earlier to take into account, for example, finite ion sizes and things like that. But sort of doing everything that we accomplished here for the batteries in that field would be amazing. And I think it's definitely doable. It's a great, it should be done. And I hope someday to do it. Maybe you guys will do it before me, but it requires having good understanding of the physics, the mathematical algorithms, and having good experimental data. It's all three have to come together to do something like this.
Yeah, the final question I have, how you have incorporated this nearest equation with the Kahn-Hillard equation. Sorry, this is like a Kahn-Hillard equation.
Oh, sure. So coming back to say this slide right here. Maybe. So specifically, how does the Kahn-Hillard equation get integrated with the reaction kinetics equations? Is that what you mean?
Yeah. So have you included any kind of reaction mechanism terms here?
Sorry, reactions? Yes. Mechanics also, yes.
So
I'm answering your question. I'm not sure I'm answering your question, but for example, here in this slide, and we have a lot more work than just this, but
how you incorporate this your ion terms with the reaction terms here that I'm bit.
So this is explained in this review paper here, and also in later work. So the Kahn-Hillard equation is basically a dynamics where the flux is it's nothing more than a conservation law for fluxes which are driven by gradients in chemical potential, which is the variational derivative of some functional. So you're basically, that's the dynamics. But the way I'm formulating the electrochemical problems here, and also various chemical problems, even without electric fields, is to say that, okay, the chemical potential to me is more than just a mathematical concept. So I think the way a lot of mathematicians, especially see Cahn-Hilliard, is that you're doing some kind of, minimization of functional, and everything is just a theoretical construct. Whereas to me, it has real physical meaning. This chemical potential is extremely important. Everything starts from that. And this is, by the way, the so-called diffusional chemical potential. So differences in this chemical potential, this variational derivative, are what leads to transport, gradients, but also it's what leads to reaction kinetics. If at an interface, if you write down a chemical reaction equation, every species in that chemical equation has a chemical potential, and you can talk about the difference in total chemical potential between the two sides of the equation. That's the so-called affinity of the reaction, or the jump in chemical potential, and that's what drives the reaction kinetics. And so various models, like for example the Butler-Volmer equation here at the bottom, or others, can be formulated in a way that is consistent, with this, sort of phase field type modeling in non thermodynamics, to account for reaction kinetics. And we can also throw in solid mechanics. We can put in charge as well, but especially the reaction kinetics has to be done in this way to be done consistently, or you're not going to get reasonable results. And one way to look at the inversion stuff I just showed you is as a validation of this entire framework, because, when I wrote my first paper on these equations, actually it was in 2006, and the paper was rejected by not a very high impact journal. I can tell you it was Electrochemical Acta, which I thought published everything in electrochemistry. And what one of the reviewers said, this is not electrochemistry. So they said, we don't understand these equations, it doesn't make any sense. And it took me a while to kind of, figure out the right way to formulate and also how to talk about it. So how to kind of go back to equations that are familiar in chemistry and electrochemistry and properly define things like activity, overpotential, et cetera, in terms of this non-equilibrium thermodynamics framework. So that's kind of what's described in this 2013 paper. Yeah. I don't know, have I answered your question?
Yeah, so I hope there will be no more further questions, and we would like to extend a warm thanks for you and a great applause for you as well.
Great. Well, thank you very much. I appreciate it.
Yeah, thank you once again, and I hope we will be really grateful for your wonderful lecture. So thank you once again. Bye. So next lecture will be started around I think 11:30. So now you can just have your high tea outside. So thank you for attending this session.
Hello, check mic. Hello, hello. Hello, hello. Check mic 1, 2, 3. Hello. Hello. Hello, hello. Check mic 1, 2, 3. Hello, hello, hello.